Okay, so let's try to make an XL6009 based boost converter. I saw these things listed on AliExpress, and it's I don't know, $2.47, $1.86 shipping. Was that $3.50 or whatever it was, 10 pieces. And note, these guys got XL semi on them. This is a genuine chip, probably. However, in typical AliExpress fashion, I think I was sent a bunch of fake chips, because the ones that I've got XLESMIL on it. And I guess if you are a little bit dyslexic, maybe you won't notice a difference, but these are obviously fake chips. They don't have XL semi on them. And anyway, I made up a circuit already, and we will see the video about how I made it up and stuff like that. But I made a little bit of changes to the circuit according to what you will see maybe in the following bit of the video, but it doesn't matter. At the end of it we will discuss that. And these chips here appear to be not running at 400 kilohertz as far as I can tell, more like 180 kilohertz, and they do have some limitations, but they do work. And I'm not sure if the genuine item would have that limitation, but probably. So these guys are a little newer than the LM2596s, and they're supposed to run at a higher frequency, but the ones that I've received, as I said, do not appear to run at 400 kilohertz, but more like 180 kilohertz. But then on the other hand, the fake LM2596s seem to be running at was it 54 kilohertz or something, as far as I could tell. In any case, the thing with this thing is that it has an input voltage of up to from 5 to 32 volts, which kind of limits their use a little bit. Initially I was thinking of using these for, before I read the datasheet properly, but using these for boosting like lithium-ion cells, which can go 3 to 4.2 volts to like 5 volts, which is the common uses of boost converters. But these things will not work for that, as you will see when we start testing it. So what these appear to be made for is for, as I said, notebook car adapters, automotive use, and stuff like that. That's why you will not find these on typical PCBs for computers and stuff like that. So they claim to have thermal shutdown and soft start and everything, but I have not actually observed some of that behavior in the chips that I have. But I'm not 100% sure, because at one stage I was running it out of spec kind of thing. It was drawing well over 3 amps, and the temperature was getting over 150 degrees Celsius. You would think that the thermal shutdown would have cut in, but in any case, this is a typical circuit that they are suggesting for a well, there's more information on that underneath this table here. The minimum input voltage they're saying is 5 volts. I have had the thing down to about 3.5 volts, but it becomes unstable after that, and if you feed it with a voltage less than 3.5 volts, the output can start generating 30 odd volts. I've seen at one stage, but most likely it'll go down to like 2 volts. But it becomes unstable and dangerous, so I wouldn't do that. And that limits its use, because if the minimum emitter voltage is 5 volts, then obviously you can't use it for a lithium-ion cell to boost its voltage. So this is I think that's the same circuit you saw before, I've repeated it here. I've made up a circuit roughly based on this circuit here, but I did make some changes. I put some extra output filtering on it. This is the circuit that I ended up putting together. The one that I'm building, that you will see straight after this, is slightly different. I had this input initially connected over here to the output of the Schottky diode, but I found a little bit. I got this extra filtering in here, and I found it beneficial to actually feed back the voltage after the filtering inductor over here. So I made that change, and I changed this resistor. Initially I put a 1K resistor and I put a 10K trim pot there, but I ended up using 330 ohms rather, and a 20K pot, but that's all. Just during experimenting, this resistor made no difference. 1K resistor, that would have been just fine. And that's my final version of the PCB. This test point is not on the one that I'm building, as you'll see, because it would be I'm taking the test straight out of this thing here, but I thought it might be handy to have that in the future version if I make any changes. So that's that. So in the next part of the video we will start building this circuit over here. For the surface mount components, I use flux, and of course we use the old MTEC, but I also use this flux, also good stuff. And this is like a paste, and it is sticky, so sometimes that's handy because you can put it on there and stick something onto the PCB, but of course as soon as you heat it, it becomes liquid, just like the other flux. And why we're using flux, obviously the solder that we use has got a rosin core solder, so it has flux in it. So for the through hole components, that is often sufficient. But when you're dealing with surface mount components, and like these guys here, the legs are fairly close together, but some of the chips that you get are way smaller, and the legs can be, less than a millimeter apart. And if you don't use flux there, you end up with solder bridges. And so that's another thing that this flux does. It actually causes the surface tension of the solder to kind of beat up, so it doesn't want to create solder bridges. And if you don't use flux, the solder can get a little bit tired, and it becomes almost a little bit like putty, and it will bridge, and it's not fluid. So that's another reason why we need to use this flux. So let's put some flux on there then. This is where the diode is going to go. Also, we're using leaded solder. If you have had any experience with the unleaded stuff, it is really nasty. It is 96 or 97% tin, and usually a little bit of copper or something has been added to it, and it has a much higher melting point, and it will not make nice, smooth, shiny joints, solder joints. Of course, commercially, you might be forced to use non-leaded solder, but and of course in the factories when they're making PCBs and so on, they will have ovens and they can sort of let it um, keep it warm for heat it for a while and let it slowly come to room temperature, and that will make the joints a lot better looking and better and stronger probably. But when you're hand soldering in the air, it cools pretty quickly and you end up usually with a grainy, gray, nasty looking solder joint. So I do not use unleaded solder, and I don't think anyone else does either in the repair or for hobby use or anything. Okay, soldering iron is up to heat. I've got it set for 325 right now. I'll see if that now when we are soldering these things, what I like to do, and I've said this many times before, but if you're watching me the first time, I tend to put solder on a pad like so on one side only, so that when you are placing the component, now let's have a look how have we got this, one side, the non-solder side, will be flush on the board. So yeah, it's got to go on that way. I'm going to turn this around for a little bit here, so I have it like that. Okay, so now I can solder the other side. I'm using 40-year-old solder here and it's still working perfectly. I used to live in Australia at that time. I'm not a native Australian. My parents immigrated there when I was about 17 years old. And there used to be a store called Dick Smith's, and this is where I bought that solder. They're defunct now. We used to compete with Radio Shack, or it used to be called Tandy over there, Tandy Electronics. Okay, so that is, just let me touch up the other side there just in case. Very good. So what's next? Let me see now. Now we have one piece of wire on there that I poked in there already. That's the, I showed before, the little, I guess I can solder up one side of that wire. I'm not soldering up this side yet until the chip is on there. See, for that I don't have to add flux. The rosin inside of the solder is already doing a good job there. Alright, so what shall we do next? How about the 1 microfarad capacitor? Now that goes over here. Okay, let's try some of that other flux there, that paste flux, so you can see how that works. See, as I said, as soon as you heat it up, it becomes liquid. Turn this around. With a solder on that side. This is actually perfect. See what I mean? The side, oops, the side that's not soldered yet is nicely flush on the copper there. If I was to put solder on both sides, then I could solder one side at a time, unless I use hot tweezers or hot air. It would be a lump over there, and then I'd have to push it down, and that's not desirable. So by starting soldering one side at a time and leaving the copper alone, it is much easier. I think I might do a video on soldering and desoldering soon. I've got some unique desoldering tools here that I haven't seen anyone else using. Okay, that's good. Now we have a 1K resistor. Where does that go? Oh, that goes up to the top here. I'm looking at my, as I said, I showed you before, the display over there. You know, I got this mechanic solder, which was advertised to be, yeah, tin leads, but it is not as good as the old stuff that I have. I don't know. That's what it looks like without flux. You see, it was all grey and nasty looking. See how it sort of goes dull? It's almost like it's lead-free solder. I wonder if they cheated. Anyway. There we are. I think I need to turn the heat up on that one. This is a ground plane. This may be part of the problem why the solder is cooling off very quickly. I think I'll use my old solder here. I think that looks good. Okay, the last little capacitor here, which actually goes over here. Some more of that paste flux, since I had some on the screwdriver there. I think I'll have to move that. Too close to the plastic in that yeah, let me rearrange. Okay. All right. Oops. Now I've got to rearrange this again. Okay, so now it's time to put this chip over here, and you might have noticed that I have on the PCB design, I actually had a clear area here that I didn't want this ground plane to be filled in with. But what I did was, when I made up the negative, I actually took a little bit of black pen and I actually colored that in, so now it actually made that pad bigger here, so that goes right to the end. So therefore, when we put this on, I can actually solder a little tab. You see, there's enough room there to do that. Another thing is that I tend to, there's several ways that I have soldered these on in the past, and that they all work okay. I will put solder down, and then I might use these two soldering irons with these spade bits, and I can actually heat both sides up at the same time, and the whole thing is set down. But today I'm going to try to do it with hot air, just for good measure. If you don't have those spade bits, you can kind of use one of these and do it like, you can either solder down one of these pins so that it doesn't move, and then use one of these things to heat up the tab until you see the solder bubbling underneath, and then that also works. So there's several different ways you can achieve this. But if we're going to do it with hot air, we will put on solder, cover it in some solder, and which is what we're going to do now. But I'm going to change, I'm going to turn on the other soldering iron with the K-tip on it. Okay, let's put some flux on. You also want to solder on that wire at the same time. Bend it over a little bit so it doesn't sag down. All right. Now hopefully when we use hot air, it will, this surface tension on the solder will pull this chip in place. Okay. I'm going to set this to 40% air so it doesn't have to blow very hard. Okay, it's up. Got to set to 350, see if that's enough. I think I might increase that a little bit. 375. I think that's already done it. Seems to be solid. Okay. Well, now I will touch up those pins to make sure that there's some good solder on there. I think that's it. also, when it comes to tweezers, I use these for other purposes other than those other ones you saw. I use these tweezers here, made in Switzerland. Now these kind of tweezers here, I got a whole bunch of these things. I seem to come for free with some stuff. The Chinese ones, I only use this for fairly crude work. They are for very fine work. They're not very good. So another hint about tweezers. But I mostly use these ceramic ones now anyway for soldering, and they're very good. Okay, so now we are going to do through hole components. But before I do that, I'm actually going to clean off the flux on the actually before I put any more components on, I am going to do some checking just to make sure that there aren't any solder bridges and things like that. And I've got the multimeter going here. Let me get these leads untangled. It'll beep. Okay, that's good. Pin 2 and pin 4 are connected together, so that's good. This should be connected to there, that's good. This is feedback. It's going to be coming from here. Okay, all's well, as expected. Alright, switch to my bigger soldering iron here. And what's first? Let's do these little guys here. Maybe not, because they're on the edge. Let's do these toroids. First the 10. This actually goes over here. Turn this around so that it matches what I'm seeing on my screen. Shouldn't have to put flux on for these. Okay. The rosin inside of the solder, it will be good enough. Okay, that's number 1. Now the second toroid here, the 33 microhenry, sits over here. Make sure that those leads are pulled all the way in. There we go. Oh, I did not want that to happen. Should have splayed out the little legs a little bit. Okay, that's better. Okay. What's next? Some capacitors. I'm using one of these solid aluminium capacitors with low ESR on the circuit here. Okay. Somehow I gotta try to keep this from falling out. I guess. See if I can tack it in a little bit here. I'll just have to put it in an angle for a second. Okay. This is a 220 microfarads, which goes over here with the positive pin on that side. And now we've got a 470 microfarad with the positive pin also on that side. Actually reusing these from another circuit, that's why the legs are already short. Makes it a little bit trickier because they can fall out when you're soldering them. Okay. On these ground planes here, the 130 watt iron is a lot more effective than the 50 watt one, as you saw from earlier. Okay, what else is this little trim pot to go in over here. Splaying out the legs a little bit so this doesn't fall out. Let's do the middle pin first. Oh, sorry, we weren't in view there. Okay, and now over here, these holes over here, we're going to put, I made up little pieces of twisted wire like that for these test points. And the idea is that this, you see this is the oscilloscope probe here. You see with the springy thingy on there. And this wire, so one will hold that little ground wire like so, and also the probe tip will go in like so they're right next to each other like that, so we don't have any ground loops there. But I want those on this side of the circuit. I made 4 of them. Actually, let's put this one over here, this one over here, and the bigger ones are for the probe tips, so they go in there, and this one goes in here, like so. You see what we have, little test points. And we can adjust those a little bit later on. Okay, let's have a look what we've got. Line these up a little bit. This one here, for instance, would go like this. like that, see? And this one over here likewise. Will go like so. Alright, so that's our test points. Now I'm gonna put these, the final thing is to put these guys on, and in order to do that I'm going to twist the board. Okay, these are those little terminals. The other one goes over here. Just double check. I make some of these holes a little bigger because they were, yeah, this fits okay there. And this clicks okay here. I'll just play those legs out just a weeny bit so that they don't fall out. Okay, so this is one of the suggested applications, like a car adapter that has an input of 12 volts and an output of 18.5 volts. So I've got it set for 19 because most notebooks and laptops, they do have 19 volt supplies. And it's suggesting that you can draw 2.5 amps, but I already know that the chip that I'm using here, the limit would be 2 amps or maybe even a little lower. I don't know. I'd have to test the temperature, but let's say 2 amps because it gets really hot otherwise. So our circuit, we actually have a little extra filtering on it, which we will look at in a minute to see how much ripple we have. So I've currently got it set for 12 volts in. It's drawing 1.7, 1.8 amps, and it's supplying 1 amp. And at 1 amp, the chip isn't even lukewarm, or you could say it is lukewarm. So, and we are getting 19.16 volts out according to the multimeter. The load says 19.04, but it's measuring that internally there might be some extra losses there, I'm not sure. And the oscilloscope showing the waveform that we have. If I increase the current, this is 1.5 amps. The voltage has dropped down to 18.90, 18.89. There's not much difference in the square wave, and in fact if you look at the square wave, it's 5 volts per division, so that's 15, 16, 17. It is actually at 18 volts. And if I go up to 2 amps, it's dropping down to about 18 volts, and for some reason we're getting a little bit of jitter on the square wave there. It has settled down. Actually, I think it can handle 2 amps pretty comfortably. I mean, if I put my finger on there, I feel heat in the middle of it, and it's uncomfortable to put my finger on there, but it's certainly not so hot that you would worry about it, and you could always put one of those little heatsink thingies on there. In any case, it seems to be working at the suggested application, but let's set it back to 1 amp, and but while the engine is running on the car, you would expect to get maybe 13.8 volts at least. And it is handling that okay, no problems at all. And in fact, you can see Ohm's law at work over here. We are actually, it is actually drawing 21 watts, and it is outputting like 19 watts. So there is a couple of watts lost there, which is the the heat in the chip and what have you. But you will notice that I'm drawing 1 amp, but the power supply is actually delivering 1.5 amps because the voltage is lower, and the lower I will make the voltage, you'll see the amperage creeping up. It's 11.9 volts. We're now at 1.8 amps because wattage is current times voltage in according to Ohm's law, so therefore that has to be met. But as I said, if we go to like 13.8 volts, it's set as for 13.5, which would not be uncommon to find on a car battery, and we're drawing 1.57 amps for a 1 amp actual draw at 19 volts. Yeah, it's working okay at that. So at higher voltages it seems to be working just fine, but again there is a limitation as to how low you can go with the input voltage. 7.5 volts. Now it is at still at 19. It is drawing 3 amps. See, now it is getting out of range. I'm feeding it 5.5 volts, and it's only supplying 13 volts out. And you can see the square wave changing. 11 volts. Still, it is working at like 12 volts, 20 volts in that region. It is working quite well as a boost converter, even though it is some sort of Chinese fake chip, and the frequency seems to be lower than what the data sheet says, but it does work. But it is not useful at low voltage applications by the looks of it, and I guess that's why there are many newer buck converter type, boost converter type controllers that probably work a lot better and at lower voltages. Anyway, it's kind of a successful build, if you like. I did make some changes to the circuit in testing, and currently I changed this resistor to 330 ohms, and I was just testing if it would be more stable. I don't think it made much difference. There was a 1K resistor there before. I changed this adjustable trim pot to 20K, and again I don't think that made much difference, except that it takes more turns in order to get the same result. And I connected the other end. It was previously connected over here, but I've connected it to the output of this 10 microhenry inductor over here, seeing if that would make a difference, and it does seem to be a little bit more stable, so I'm leaving it there. Okay, well, it looks like at 19.4 volts out, the ripple is around 50 odd millivolts, as you can see it on the screen there, which is probably acceptable for a voltage like that. If I increase the current, doesn't seem to go up at all. Let's go right up to 2 amps. And 2 amps, it's a little bit more, 80, 90 millivolts. Yeah, 1 amp, back to 50 odd millivolts. I think that is actually quite good. If you look at the actual voltage, it's 5 volt per division. Oh, let's even go to 1 volt. It's hardly noticeable at all. Okay, so anyway, I think it is somewhat of a successful build, depending what you're planning to use this for. As a car adapter, in actual fact, it would work quite well, and that's its intended application by the looks of it. It is not useful for boosting, let's say, a single lithium ion cell that can go right down to 3 volts up to 5 volts. For that we will need a different kind of chip. Maybe in future I will check some of those Motorola ones out. The really modern ones, they run at 1 megahertz or something like that, and I think they can do it. But these XL6009 chips, also, they're getting a little older, and obviously they were not aimed at that sort of application. In any case, so much for that. If you like these videos where I'm investigating the limitations of these devices and how you can use them in circuits, make sure to subscribe and like and ring the little bell thing and all that kind of stuff at the end. And I will put a list of all the equipment that I use in order to build these things in the description. So I'll see you guys later.